Welcome back. In the last few lectures I have discussed how to estimate heat transfer through buildings, like through opaque walls, through fenestration, and heat transfer due to infiltration, ventilation, etc. So in this lecture I shall discuss the methods of estimation of cooling and heating loads on a particular building and how to estimate the required cooling or heating capacities using the information provided in the last lectures. Okay, so the specific objectives of this particular lecture are to discuss estimation of internal and external sensible and latent cooling loads on the building, estimation of required capacity of the cooling system, difference between cooling and heating load calculations. At the end of the lecture you should be able to estimate sensible and latent cooling loads on the buildings due to external and internal sources using CLTD, SHGF, SC and CLF tables and design data and building specifications, and estimate cooling capacity of the system from the above information, and differentiate between cooling and heating load calculations, and finally estimate heating loads assuming steady state conditions. So let me give a brief introduction. Heating and cooling load calculations involve a systematic stepwise procedure to estimate the required system capacity considering all the building energy flows. As you know, cooling load calculations are carried out to estimate heat gain during summer and to find out the required cooling capacity of the system, whereas heating load calculations are carried out to estimate heat loss in winter and find out the required heating capacity. And load calculations are carried out based on a set of known input data. Heating load calculations can be carried out assuming steady state conditions, as the peak heat load occurs before sunrise and outside temperatures remain fairly constant during winter months. And also you can neglect internal heat sources while estimating the heating loads, because these internal heat sources partly offset the heat losses. However, for cooling load calculations you must consider the unsteady state because of the presence of sun and varying outdoor conditions, and we also have to consider the internal heat sources as they increase the heat gain. As a result, you find that the cooling load calculations are invariably more complicated than heating load calculations. So in this lecture I shall first discuss in detail the cooling load calculations, and the procedure for heating load calculations are almost similar and it is much simpler than this. Okay. Now let us look at the methods of estimating cooling loads. The easiest method is what is known as based on rules of thumb, using CLTD and CLF method, using transfer function method, etc. First let us look at the rules of thumb. For example, this particular table shows the required cooling capacity for various applications. For example, you can see here that for an office building, and if it is an external zone and if it has 25% glass, the required cooling capacity is about 3.5 TR, okay, for 1000 square of floor area, okay, 1000 feet square of floor area. If the percentage of glass is 50%, then the required cooling capacity is about 4.5 tons and so on. Similarly, for other applications, for example computer rooms, the required cooling capacity lies in between 6 to 12 tons per 1000 feet square of floor area. Similarly, for other applications like hotels, bedrooms, departmental stores, shops, banks, theaters, etc. Okay. So these are based on the long years of experience, and these values are arrived at, as I said, many years of experience. Okay. So these are what is known as estimating the cooling capacity based on rules of thumb. You will notice that rules of thumb, they are very useful for preliminary estimation. However, they are not recommended as they do not consider design aspects of the specific building. Okay, so rules of thumb are used only for preliminary estimation, not for final calculations. The CLTD CLF method, which is basically suggested by ASHRAE, it is widely used as it is simple and it also consumes less time. The transfer function method is more accurate, but it is more time consuming, hence it is generally used for large commercial buildings. In this lecture I shall discuss mainly the CLTD CLF method. So cooling load calculations based on CLTD CLF method. The cooling load experienced by a building varies in magnitudes, it does not remain constant, it varies in magnitude, and the variation can be from 0, that means no cooling is required, to a maximum value. And the design cooling load is a load near the maximum magnitude, but is not normally the maximum. Okay, it is near the maximum but not the maximum. Design cooling load takes into account all the loads experienced by a building under a specific set of assumed conditions. Okay, so what are the conditions based on which the cooling load calculations are carried out? First, the design outside conditions are selected from a long term statistical database. The conditions will not necessarily represent any actual year, but are representative of the location of the building. Next, the load on the building due to solar radiation is estimated for clear sky condition, that means we do not take into account clouds. Okay. The third point, the building occupancy is assumed to be at full design capacity. And finally, we assume that all building equipment and appliances are considered to be operating at a reasonably representative capacity. So, these are the conditions based on which we carry out the cooling load calculations. And each and every element of the building that contributes to the building energy flow must be considered for load calculation. So, we have to take into account all the elements of the building. The total building cooling load consists of external loads and internal loads. Again, both external and internal loads consist of sensible as well as latent components. Let me show this with the help of a schematic. For example, what is shown here is a typical building. So, it is subjected to solar radiation. So, heat transfer takes place to the building because of solar radiation through opaque surfaces, through fenestration. Okay. Similarly, heat transfer also takes place from the ground. Heat transfer takes place due to infiltration. Infiltration heat transfer consists of both latent as well as sensible. Okay, latent plus sensible. These are the external loads. In addition to this, we also have internal heat sources. For example, the people inside the conditioned space, they add load to the building. Okay, so these are what is known as internal heat sources. In addition to people, we may also have several appliances, equipment, etc. Okay, so all these constitute internal heat sources. So you can see that a building is subjected to external loads as well as internal loads. Buildings in general may be either externally loaded or internally loaded. So, what do we mean by externally loaded building or an internally loaded building? In externally loaded buildings, the cooling load on the building is mainly due to heat transfer between the surroundings and the internal conditioned space. Since the surrounding conditions are highly variable, for example, outside solar radiation, outside temperature varies widely in a given day, the cooling load of an externally loaded building varies widely. Okay. So, this is a typical characteristic of an externally loaded building. In internally loaded buildings, the cooling load is mainly due to internal heat generating sources such as occupants or appliances or processes. Since the load does not depend very much on the highly variable outdoor conditions, the cooling load of an internally loaded building does not vary widely. For example, consider a theater. Okay, a theater can be treated as an internally loaded building because the heat generation due to the occupancy inside the building generally is much higher than the external loads. So, you find that irrespective of the outside conditions, the load on the building remains more or less constant, okay, which depends upon the occupancy, right. So, the knowledge of whether the building is externally loaded or internally loaded is essential for effective system design. It helps if we know beforehand whether it is externally loaded or internally loaded. Now, let us look at estimation of external loads. First, we take, as I said, we have to consider all the elements. First, we take heat transfer through opaque surfaces. Opaque surfaces means all the walls, roof, floor, doors, etc. Okay. So, the heat transfer rate through these opaque surfaces is sensible heat transfer only, you do not have any latent component, and the heat transfer rate is given by Q is equal to U into A into CLTD, where U is the overall heat transfer coefficient of that particular element, A is the area of that particular element, and CLTD is the cooling load temperature difference, as we have seen in the last lecture. And for sunlit walls and roof, CLTD has to be obtained from CLTD tables. This we have discussed in the last lecture, how to estimate the cooling load temperature differences for using the tables. Let me show a typical table here. For example, this particular table shows the CLTD values in degrees centigrade or degrees Kelvin for a D type vertical wall. I have defined what is a D type vertical wall in the last lecture. Okay, so you can see here that here the cooling load temperature difference is given at different solar times, okay, starting with 7 o'clock in the morning to about 8 o'clock in the evening, and for different orientations of the wall. For example, if it is north facing, northeast facing, east facing, southeast facing, etc. Okay, and you can see here that for a particular orientation the cooling load temperature difference varies with time. For example, for a north facing wall it increases, okay, it reaches the maximum of 11 degrees at about 8 p.m. Okay, whereas for a northeast face wall again the temperature difference varies and it reaches peak between 5 to 7, right, and for an east facing wall the peak occurs around noon, right. Similarly for other orientations, and in this table what is given is CLTD maximum is also given, okay, for a particular orientation what is the maximum value of cooling load temperature difference. Now if you want to estimate the heat transfer rate through the building walls, okay, a building may consist of 4 walls, let us say, and I would like to find out what is the, and let us say that all these 4 walls are external walls, that means they are all exposed to outdoors, that means they are sunlit walls and they are also exposed to outdoor air. So if I would like to find out what is the total heat transfer through all these walls. As you have seen from the table, the CLTD values for a particular orientation varies with solar time, and it reaches a maximum at a particular time for a particular orientation, and the maximum CLTD value for all walls does not occur at the same time. Obviously for east facing wall it occurs much earlier compared to a west facing wall. So it is generally advisable to calculate the heat transfer rate at different times. For example, I start the calculations at 8 a.m. let us say. So at 8 a.m. I find out what is the cooling load temperature difference for all the sunlit walls, and multiply that into UA of the respective wall and find out the total heat transfer rate through all the walls. Then I also do these calculations at 9 a.m., at 10 a.m. like that, okay. Like that I continue the calculations maybe till 6 or 7 p.m. in the evening. Then I add up the total heat transfer rates. That means I find out what is the total heat transfer rate at 8 o'clock in the morning, 9 o'clock in the morning, 3 p.m., 4 p.m. like that, okay. And obviously these values will be different for different times. So what I have to do is I have to select the maximum value for fixing the system capacity, okay. The maximum value not necessarily occurs when all of them are maximum, okay, because all of them do not reach maximum value at the same time, okay. So generally it is you have to prepare some kind of a spreadsheet, okay, and calculate for east facing wall 8 a.m., 9 a.m., 10 a.m. what is the heat transfer rate, for west facing wall what is the heat transfer rate at different times, add up and see what is the maximum heat transfer rate, and that is taken as the design cooling load on the building through the walls, okay. So these CLTD values and CLTD tables have to be used for all sunlit walls and roof. And how about other elements, for example, which are not sunlit? For other elements which are not sunlit or which have very small thermal capacity, for such as doors, windows, internal walls, floor, etc., the CLTD is simply equal to the temperature difference across the elements. So here you do not have to consider the solar radiation aspects, etc., because either they are not sunlit or they have very small thermal capacity, hence they do not store much energy, okay. So for these elements the heat transfer rate is simply equal to UA into temperature difference. For example, for an external door Q is equal to U into A into T out minus Ti, where T out is the design outdoor temperature and Ti is the design indoor temperature, okay. That is how you have to find out heat transfer rate through all the opaque elements of the building. Next comes heat transfer rate through fenestration. Fenestration, as I said, is transparent surfaces such as windows, etc. For heat transfer through fenestration, this includes heat transfer by conduction due to temperature difference across the window, and also heat transfer due to solar radiation through the window. So it consists of 2 components. Again, this is sensible in nature, okay. So for here heat transfer by conduction is simply given by Q is equal to U into A into T naught minus Ti, where U is the overall heat transfer coefficient for that particular window and A is the surface area of the window, and T0 and Ti are the design outdoor and indoor temperatures. This is only one part. The second part is heat transfer due to solar radiation. This is given by Q is equal to A unshaded into SHGF max into FV into CLF. These aspects we have discussed in the last lecture. In this particular expression, A subscript unshaded is the unshaded area of the window. Okay, if it has any external shading devices such as overhangs, you have to find out the unshaded area and you have to use that area, not the total area. And SHGF max is the solar heat gain factor, maximum solar heat gain factor. FV is the shading coefficient, which takes into account the different types of glass and also any internal shading devices such as curtains, etc. And CLF is what is known as cooling load factor. And we have seen in our earlier lecture that the values of SHGF max and shading coefficient FV are available in the form of tables. Let me show typical tables which I have already shown earlier. For example, this particular table gives the maximum solar heat gain factor for sunlit glass located at 32 degrees north latitude, and the units are watt per meter square. Okay, here the maximum value is given for different months, for December, starting from January to December, for different orientations of the window. Okay, for example, if the window is north facing or if it is in shade, these are the values to be used. Okay, and for other orientation, these are the typical values to be used. If you are carrying out the calculations for summer, typically we consider these months either from May to July. Okay, so you have to take either one of these two values depending upon where the design temperature is likely to be maximum. Okay, this is a table for SHGF max, and such tables for different latitudes are available in ASHRAE handbooks. Next table shows the shading coefficient values. As I have already said, the shading coefficient considers the type of the glass, okay, whether it is a single regular glass or whether it is heat absorbing glass or double glass, right, and for different thicknesses. And if you do not have any internal shading, this is the shading coefficient value, and if you have any internal shading such as Venetian blinds or roller shades, these are the shading coefficient values to be used. Okay. So, this is as far as your shading coefficient and SHGF max is considered. Then what is cooling load factor? The cooling load factor CLF accounts for the fact that all the radiant energy that enters the conditioned space at a particular time does not become a part of the cooling load instantly. Radiation heat transfer introduces time lag depending upon the dynamic characteristics of the surface. So, what happens when radiation enters into a conditioned space? Let us say that you have a window exposed to the outside and solar radiation enters into the conditioned space through the window. Okay, since it is radiation, the air inside the building does not absorb all this radiation. Okay, only a small fraction of this is absorbed by the air. Most of it is absorbed by the surrounding surfaces. For example, the walls, floor, roof. If any furniture is there, that also absorbs this radiation. So, first the radiation is absorbed by the walls and the other surfaces and not by the air. Okay. So, as a result, when radiation first enters into the conditioned space, the conditioned air temperature does not increase immediately. Okay. So, what happens is first all these surfaces absorb solar radiation, as a result their temperature increases depending upon their thermal capacity. Okay, when their temperature goes beyond the conditioned space temperature, then there will be heat transfer by convection from the internal surfaces to the conditioned air. Only when this heat is transferred to the conditioned air, then only it becomes a part of the cooling load on the building. Okay, not when it enters into the building. Okay, so that means you can see that there is a time lag, that time at which the solar radiation enters into the building and the time at which it is transferred to the air. Okay. So, this time lag is coming because of the radiation factor. Okay. So, this time lag is taken into account by introducing a factor called as cooling load factor. Okay. The radiation may also introduce a decrement. For example, if the surrounding surfaces are absorbing the radiation and a part of it may be transferred to the outside air, not to the inside air. Okay. So, all these aspects are clubbed into a single factor called as cooling load factor. If you do not consider cooling load factor, or if you take the cooling load factor as 1, that means you will be overestimating the heat transfer or overestimating the cooling load. Okay. Another peculiar aspect of this radiation heat transfer is that even when the source of radiation is removed, still you feel the effect of the source. That means even when sun sets, still inside the building it will be warm, okay, because of the time lag. Okay, so this is the typical characteristics of radiation. Now, due to the time lag, the effect of radiation will be felt even when the source of radiation, in this case the sun, is removed, okay, as I have already explained to you. The CLF values for various surfaces are available in the form of tables, okay. So, these tables have been obtained from experimental measurements, etc. So, for example, this shows a typical table for cooling load factors for glass with interior shading, and this is applicable to north latitudes. Okay, so you can see that for glass with interior shading and for north latitude. Okay, so here again you can see that the CLF, these are all the CLF values. Okay, you can see that everywhere it is less than 1, right, and this is a function of the solar time. Okay, so it varies with solar time, and it also varies with the orientation of the window. Okay, so if you are calculating radiation heat transfer, just like CLTD, what you have to do is you have to calculate heat transfer rate at different times, let us say at 9 am, 10 am, 11 am, etc. Okay, then you have to calculate different times for all the windows, that means windows in different orientations, and then you have to calculate what is the total heat transfer rate due to solar radiation at 9 am, 10 am, 11 am, etc., and you have to select the maximum value, okay, for system capacity estimation. Okay. So, as I said, this kind of tables are available in several handbooks such as ASHRAE handbooks and all for different conditions. Okay, for example, as I said, this is with interior shading. Okay, without interior shading, you will have different values of cooling load factor for glass. Okay. Next comes heat transfer due to infiltration. Heat transfer due to infiltration consists of both sensible as well as latent components. Okay, when outside air enters into the building, it brings along with it both sensible heat as well as latent heat in the form of moisture. Okay, so due to ventilation as well as infiltration, you have sensible and cooling loads being added to the building. Okay, so we have to find out what is the amount of sensible heat transfer to the building because of infiltration, and we also have to find out what is the latent heat transfer to the building because of infiltration. Okay. The sensible heat transfer rate due to infiltration is given by Q subscript S infiltration is equal to m dot subscript O into CPM into T naught minus Ti, which is written in terms of volumetric flow rate. This is your volumetric flow rate, so many meter cube per second, okay, multiplied by the density of the air. CPM is the specific heat of the moist air, and T naught and Ti are the outdoor and indoor design temperatures. Okay. So, if you know the design outdoor and indoor temperatures, and if you know what is the infiltration rate, you can find out what is the heat transfer rate, sensible heat transfer rate due to infiltration. Similarly, the latent heat transfer rate due to infiltration is given by this expression. This is the latent heat transfer rate due to infiltration, which is equal to infiltration, the mass flow rate of infiltrated air multiplied by the latent heat of vaporization for water multiplied by the humidity ratio difference, where this is the outdoor humidity ratio, this is the indoor humidity ratio. Okay. Again, this is written in terms of the volumetric flow rates, right. So, if you know the infiltration rate, then you can easily calculate what is the heat transfer rate due to infiltration. Of course, the main problem is how to estimate the infiltration rate. The infiltration rate is obtained by either the air change method or the crack method. Okay. This also I have discussed in the last lecture, in one of the lectures. Infiltration by air change method is given by this formula, infiltration rate, okay, in meter cube per second, right, is given by ACH multiplied by V divided by 3600, where ACH is the number of air changes per hour and V is the gross volume of the conditioned space in meter cube. Okay. Since air changes are per hour, we have to divide by 3600 to get meter cube per second. Okay. And these ACH values, it is observed that the air change values vary from 0.5 ACH for tight and well sealed buildings to about 2 for loose and poorly sealed buildings. Okay. And it can be as low as 0.2 for modern buildings which are very tight. Okay. The modern buildings are generally designed not to allow any outdoor air. So, that means they have very small infiltration rates. Okay. So, knowing the infiltration rate from air change method, from air changes you can calculate what is the heat transfer rate due to infiltration. Of course, how do you decide whether the building is well built, tightly sealed, or what should be the value of ACH to be used? Okay, generally the value of ACH depends upon the condition of the building. If the building is old, okay, and if it is not properly sealed, that means the windows and all, there are a lot of air gaps, then obviously the ACH value will be higher. Okay, so you have to use some experience in choosing a proper value for ACH. Okay. The next method, as I said, is what is known as infiltration rate by the crack method. Okay, so this is given by again the infiltration rate here. This is the infiltration rate in meter cube per second. This is equal to A into C into delta P to the power of n. Okay, and it is in meter cube per second. What is A? A is what is known as effective leakage area of the cracks. Okay, the units are meter square, and C is a flow coefficient which depends upon the type of flow. That means type of the air flow through the cracks. Okay, so depending upon the type of flow, the value of C varies, and n is an exponent which again depends upon the type of the flow. Okay, and its value lies between 0.4 to 1. Okay, and what is delta P? Delta P is nothing but the pressure difference between the outdoors and indoors. So delta P is equal to P naught minus Pi, where P naught is the outside pressure and Pi is the inside pressure, and it is seen that delta P is equal to a summation of pressure difference due to stack effect, pressure difference due to wind effect, and pressure difference due to building pressurization. Okay, delta P this particular this is the pressure difference due to building pressurization. That means if the building is pressurized, there will be a pressure difference. Okay, and I have explained what do you mean by stack effect and wind effect in the last in one of the lectures. Okay, stack effect occurs due to temperature difference between the indoors and outdoors. So this is also known as chimney effect. Okay, because of the temperature difference, there will be some buoyancy effect, and because of the buoyancy, there will be mass transfer between the outdoors and indoors. Okay, air enters or leaves because of this. And the wind effect, when wind is blowing over the building, that means outside, this also introduces a pressure difference. Okay, so this is a pressure difference due to wind, right? So the total pressure difference between the conditioned space and the outdoors is a summation of pressure difference due to stack effect, pressure difference due to wind effect, plus building pressurization. Okay, and semi-empirical methods are available for estimating delta P stack and delta P wind. Actually, the estimation of delta P due to stack effect and delta P due to wind effect analytically can be very complicated. Okay, because this depends upon the construction of the building. Okay, and the direction of the wind also may vary, and wind is highly variable. Okay, so analytical estimation of delta P because of these two factors can be quite complicated. Okay, however, semi-empirical methods are available using which one can estimate the pressure difference because of these two effects. Right, once you know the pressure difference and once you know what is the type of flow, then you can calculate what is the infiltration rate. Of course, you also have to know what is the area of the crack, which is again difficult. Okay, so what is done in practice is for different types of windows, doors, buildings, etc. The infiltration rates have been measured. Okay, as a function of temperature difference, as a function of the wind velocity, etc. And they are available in the form of tables. Okay, so knowing the outdoor and indoor temperatures and knowing the wind velocity, one can estimate the infiltration rate depending upon the type of the window. Okay, that is what is generally done while estimating infiltration rates. Next, in addition to all these factors, if the cooling coil has a positive bypass factor, then some amount of ventilation air directly enters the conditioned space, in which case it becomes a part of the building cooling load. Let me explain this. What is shown here is an air conditioning system, right? So you have the conditioned space here, and we are right now we are finding out what is the total heat transfer rate to the conditioned space. Okay, sensible as well as latent. And ventilation, if you remember, I have discussed this earlier. Some amount of ventilated air is required for indoor air quality. So generally what is done is this outdoor air is mixed with some amount of recirculated air, then it is processed in the cooling coil, and the processed air is supplied to the conditioned space. Okay, but normally all cooling coils will have some bypass factor. Okay, this bypass factor will be in general greater than 0 and it will be less than 1. Okay, So, because the bypass factor, what happens is some amount of outdoor air does not flow through the cooling coil, but it bypasses the cooling coil and directly enters into the building. Okay. So, it is not rejecting its heat to the cooling coil, but it is rejecting its heat to the conditioned space, in which case it becomes a part of the cooling load of the building, not a cooling load of the coil. Okay. I will show the difference between the load cooling load on the coil and cooling load on the building in a later slide, right. But you have to keep in mind that if you have a non-zero bypass factor, you must consider that while estimating the load on the building. Okay. So, how do we estimate the latent and sensible heat transfer rates because of this bypassed ventilated air? So, it is very simple. The sensible and latent loads due to the bypassed ventilation air are obtained using the values of ventilation rate, bypass factor, and using expressions similar to that of infiltration. All that you have to do is you have to replace the infiltration rate with this quantity. Okay, you have to replace it with this quantity, and this quantity is nothing but the flow rate of air bypass ventilated air. Okay, that is what you have to do. In addition to this, if the supply duct consists of supply air fan with motor, then power input to the fan becomes a part of the external sensible load on the building. Okay. You have seen that normally a supply duct consists of a fan, and supply duct, even though it is insulated, it is not possible to perfectly insulate the supply duct. So, the inside temperature, that means the temperature of air inside the supply duct will be much less than the temperature outside. Okay. So, as a result there will be some heat transfer from the outside to the inside air through the insulation. Okay. This is sensible heat transfer. In addition to that, if the supply air duct has some leakages through which air is escaping, okay, this is also a loss, right, and this becomes a part of the external load on the building. So, these factors also have got to be considered while calculating the external load on the buildings. Okay. How do we consider this? The problem here is that since the power input of the fan is not known beforehand, what we normally do is we assume that the supply fan adds about 5% of the room sensible cooling load, because initially we do not know what is the power input of the fan, right, because we have not yet selected the fan. How do we select the fan? We select the fan depending upon the flow rate. So, at this moment we do not know what is the required air flow rate, because we have not yet estimated the total load on the building, right, but the fan power is a part of the building load. Okay. So, what is normally done is initially we assume that the fan adds about 5% of the total cooling load on the building. Okay. So, you multiply the building cooling load by 1.05, okay, where 0.05 takes into account the heat added due to the fan, right, and you do the regular load calculations, and at the end when you know what is the supply air flow rate, then you can select a fan, and then again you can refine this value by taking the actual fan power consumption into account. This is what is generally done. Okay. Similarly, this is what I have mentioned. Similarly, a safety factor is provided to account for leakage losses through supply duct, which are part of the external load. Okay. Again, external leakage losses through supply duct, this is also difficult to estimate at this point, because we do not know what is the size of the duct. So, we will see in a later lecture that the size of the duct has to be decided depending upon what is the required flow rate. Okay. So, since we do not know the flow rate at this point, we cannot find out what is the losses through the supply duct. So, what we do is we add, or we take a safety factor which will account for heat losses through the supply duct, and which can be again refined in the end when you have all the other values. Okay. Now, we have seen all the external loads. Now, let us look at internal loads. How do you estimate cooling load due to internal heat generating sources? What are the internal heat generating sources? First internal heat generation source is the occupant himself. Okay. So, what is the load due to occupants? As we know, the load due to occupants consists of both sensible as well as latent components. Okay. Because sensible heat transfer because of heat transfer between the human body and the surrounding air, latent heat transfer because of evaporation and respiration from the body. Okay. So, sensible load due to occupants is given by a number of people multiplied by sensible heat gain per person multiplied by CLF. Okay, where CLF is a cooling load factor. Why are we using a cooling load factor here? We have to use, strictly speaking, we have to use cooling load factor because the heat transfer rate, sensible heat transfer rate from a human body to the conditioned air takes place by convection as well as radiation. Okay, you also have a radiation here. The moment you have radiation, again it does not become an instantaneous load on the building. Okay, again there is a time lag. So strictly speaking, if you want to find out what is the sensible heat transfer rate from the occupants, you have to consider the CLF for the occupants, cooling load factor, just like radiation through fenestration. Okay. Next comes latent load due to occupants. Latent load due to occupants is given by number of people in the occupied space multiplied by latent heat gain per person. Okay. Here you do not use any cooling load factor, because the latent load is an instantaneous load, because the moisture is instantaneously added to the surrounding air and it becomes an instantaneous load. So, you do not have to use any CLF value. Okay. And typical values of heat gain from occupants and CLF values are available in the form of tables. Okay. Let me show a simple table. This table here shows what is the total heat gain per person, okay, as a function of activity, right, for different activities. Okay, so this is the activity, this is the total heat gain per person, right, 70 watts per person, 100 watts per person, like that, and out of this what fraction of it is in the form of sensible heat and what fraction is in latent heat. Okay. For example, if the person is sleeping, that means if the occupied space consists of people who are sleeping, then heat gain per person is given by 70 watts, and out of this 70 watts 75% is in the form of sensible heat and 25% is in the form of latent heat. And if the occupants are seated, okay, then they release about 100 watts of heat per person, and out of this 60% is in the form of sensible heat and 40% in the form of latent heat. Similarly, for different activities, for example, the conditioned space has people who are walking at a rate of 3.5 kilometer per hour, then they release much larger amount of heat because of higher activities. So, you find that about 305 watts per person is released, and out of this only 35% is sensible and 65% is latent. Okay. Similarly, for other activities, for example, industrial work, lot of heat is released, about 300 to 600 watts per person, and out of which only 35% is sensible and 65% is latent. Okay. This kind of information for a wide variety of activities are again available in air conditioning data handbooks. Okay. And one thing here you must keep in mind is that the fraction of the total heat gain that is sensible, that means this factor, okay, this depends very much on the conditions of the indoors. Okay, if the indoor temperature increases, then the sensible heat gain fraction decreases and latent heat gain fraction increases, okay, and vice versa. And again this kind of information is available, what is the sensible heat gain fraction as a function of the indoor conditions, okay, that information is also available in handbooks, right. Next comes the CLF value for occupants. CLF value for occupants are also available in the form of tables, and this depends on the hours after the entry of the occupants into the conditioned space, the total hours in the conditioned space, and the type of the building. Okay, so depending upon all these factors, the CLF values have been obtained. You will appreciate the use of CLF factor. We know from common experience that let us say that you have a theater, okay, and a lot of people are there in the theater and the surrounding air becomes warm. Okay. So, even when all the people leave the theater, still the temperature inside the occupied space continue to increase because of the time lag, right. This is because of the fact that the human beings release heat, sensible heat, in the form of radiation as well as convection. Okay. So, all that radiation portion is absorbed by the building, surrounding building, and it is slowly released. Okay. So, as a result you feel the effect even when there are no occupants. Okay. So, this factor is taken into account by the CLF factor. Okay. In some of the air conditioning load estimation methods, the CLF is simply taken as 1, that means they do not consider the radiation effect. So, if you do not consider the radiation effect and take CLF as 1, normally you will be slightly overestimating the required cooling capacity. Okay. Of course, if you do not have any information, it is always better to take a CLF value of 1. So, this is the heat load due to occupants. Next comes load due to lighting. Lighting adds sensible heat to the conditioned space, and we know very well that the heat added by lighting is mainly, if it is a incandescent lamp, it is in the form of radiation. So again you have to use a cooling load factor. Okay, so a cooling load factor is used to account for the time lag due to radiation from the lights, and the total heat transfer rate due to lighting is given by this expression: Q lighting is equal to installed wattage multiplied by UF multiplied by BF multiplied by CLF, where installed wattage is the total amount of lighting, that means so many watts of lights inside the conditioned space. And what is UF? UF is known as a utilization factor, and the value of UF lies between 0 to 1. What is the utilization factor? Utilization factor is that at the time of load calculations, all the lights in the building may not be on, okay, only few lights may be on. So if you take the installed wattage, then you will be overestimating the required cooling capacity. For example, if you are doing the load calculation for daytime, okay, and if it has considerable natural light, then most of the lights may be off, right? Then there is no point in considering the wattage of all these lights because they are not on, so they are not load on the building. Okay, so if you want to be more accurate, you must consider the utilization factor. Okay, which as I said is lies between 0 to 1. Then comes the ballast factor, BF. BF is known as ballast factor, and the ballast factor is 1.25 for fluorescent lamps, and it is 1 for incandescent lamps. That means the lamps with choke you have to take 25% higher than the rated wattage, whereas for incandescent lamps which do not have any choke, the ballast factor value is 1. And CLF, as I said, is a cooling load factor, and cooling load factor for lights that is again available in tables as a function of the type of fitting, I mean what kind of light fitting it is, and the number of hours of operation, that means how many hours lights are on, and time after the lights are switched on, and type of the building. Okay, so depending upon all these factors, the CLF values have been obtained and they are available in the form of tables. Okay, so using the table and using suitable values, you can find out what is the load due to lighting. Of course, the load due to lighting is purely sensible, you do not have any latent component. Okay, load due to lighting can be considerable, especially in modern buildings which do not have any external windows. Okay, so one should not neglect this, one must consider load due to lighting. Okay. Next comes internal load due to equipment and appliances, and when in a conditioned space may consist of many home appliances or several equipment such as computers, printers, etc. All these generate heat, and this heat is added to the air inside the conditioned space, and it has to be ultimately taken out from the building. Okay, and this load can be sensible and latent depending upon the type of the equipment. And how do we estimate the sensible load due to appliance or equipment? It is simple, it is given by Q sensible load due to appliance or equipment is equal to rated wattage multiplied by the utilization factor UF multiplied by the cooling load factor. Here again you can have a cooling load factor because some of the sensible heat from the equipment or appliance may be in the form of radiation. For example, if you have an oven or if you have an electrical heater inside the conditioned space, then most of the heat may be in the form of radiation, in which case you have to consider the cooling load factor. Okay. Again, as I said, UF is the utilization factor. And then what is the latent load due to appliance or equipment? Latent load due to appliance or equipment is given by the rated wattage multiplied by the utilization factor multiplied by the latent heat fraction. That means how much heat, how much of the total heat is in the form of latent heat. Okay. For example, if you have a pressure cooker, okay, then there may be a lot of moisture addition to the conditioned air. Okay, in which case the appliance is adding a lot of latent heat to the conditioned air, so you have to treat that separately. Okay, so one must have information about this. Even though the equations for estimating internal loads, for example, for occupants, for lighting, and for appliances, appear to be quite similar, quite simple. Okay, they are simply multiplication of wattage and utilization factor, etc. In actual case, it could be quite complicated because of the fact that the utilization factor may vary widely. Okay, so precise knowledge about the utilization factor is generally not available. Okay, most of the time you have to make an intelligent guess and use a proper utilization factor. If you are taking a utilization factor of 1 and taking a cooling load factor of 1, as I said, you will be overestimating the capacity, right. On the other hand, if you are taking too small a value, then you will be underestimating the capacity and the system may not be adequate. Okay, so this is what brings in the difficulty. And typical appliance loads are available in the form of tables. Let me show a typical table. So, this table is taken from Professor Arora's book, and here I have just shown the 4 appliances. A coffee brewer of 0.5 gallon capacity, it rejects about 265 watts of sensible load and about 65 watts of latent load, and the total load of this particular appliance is 330 watts. Okay. And a coffee warmer of 0.5 gallon capacity, it rejects about 71 watts in the form of sensible heat and 27 watts in the form of latent heat. If you have a toaster of 360 slices per hour, then the sensible load is about 1500 watts and the latent heat load is 382 watts. And for example, a food warmer, it is 1150 watts of sensible load per meter square of the plate area and 1150 watts of latent heat load per meter square of plate area. So, total heat addition is 2300 watts. Okay. And appliance loads of many other household and office appliances and equipment are available in ASHRAE handbooks. In fact, if you look at ASHRAE handbooks, it covers a wide variety of all kinds of home appliances and office equipment. Okay. In addition to that, if the conditioned space is used for storing products, for example, if you are doing the load calculations for cold storage, then you will be using the conditioned space for storing food products. For example, I am designing a cold storage for storing potatoes. Okay, the potatoes are live products, so they will be adding continuously heat to the conditioned space. So, I should be able to estimate what is the heat generation rate because of the products stored inside the conditioned space, in this case potatoes. It could be potatoes or it could be anything, right. So, I should be able to know what is the amount of sensible heat generated because of this and what is the latent heat generated, okay, because of the product stored in the conditioned space. Again, a lot of information is available on the amount of heat released in sensible as well as in latent form by a wide variety of products which are normally stored in cold storages. Okay. So, you can look at any air conditioning design or refrigeration design data book. So, you find that this information is available. Okay. So, this is very important for estimating the loads of cold storages and other industrial or commercial air conditioned buildings. Okay. In addition to this, if some process is taking place inside the conditioned place, okay, let us say that we are talking about air conditioning of a chip manufacturing factory. Okay. So, the lot of processes will be taking place inside the conditioned space which will be adding heat, okay, either sensible or latent or both. So, again we must have information and we must have knowledge about how much heat is being added by all these internal processes for estimating the loads. Okay. So, you can see that for load calculations a large amount of input data is required, okay, reliable accurate input data is required, only then you can have accurate estimations of the loads. Okay. Using the above equations, one can estimate the sensible total sensible load on the building, total latent load on the building and total cooling load on the building. Total cooling load on the building is nothing but sum of sensible loads and latent loads. Okay. So, what do you mean by total sensible load on the building? Sensible load due to external sources, sensible load due to internal sources. We have to add up all this. So, that will give you the total sensible cooling load on the building. Similarly, we have to add up all the latent cooling loads on the building, both internal as well as external. Okay. We have seen individual loads, we have to add up now and that will give you the total loads, and when you add up everything you get the total cooling load on the building. Okay. And from the sensible and total cooling loads, one can calculate the room sensible heat factor RSHF for the building. Okay. These aspects we have discussed in our earlier lectures. The room sensible heat factor, as you know, is nothing but the ratio of the total sensible load on the building divided by the total load on the building. Okay. So, since you have got all this information from the load calculations, you can calculate now what is the RSHF of the building. Okay. And as discussed, from the RSHF value and the required indoor conditions, one can draw the RSHF line on the psychrometric chart and fix the condition line of the supply air. So, okay, at this point, since we know the RSHF and we also know the inside conditions, you can draw the RSHF line, and as you know, the supply conditions must lie on this RSHF line, so that it can meet the sensible and latent loads in the required proportion. Okay. So, at this point you can draw the process RSHF line, okay, from this information. Now let us look at the estimation of the system cooling capacity, because ultimately we are interested in finding out what is the required cooling capacity of the system. Okay. To find the required cooling capacity of the system, one has to consider the sensible and latent loads due to ventilation and leakage losses in return air ducts. Okay. So let me show a picture, it will be clear. Again, this is the picture what we have discussed earlier. You can see that this is the building, and this building is subjected to some amount of sensible heat load and some amount of latent heat load, and I am interested in finding out what is the required capacity of the cooling system. That means what is the amount of heat that has to be rejected in the cooling coil, that means this. Okay. What is this? This we will see later that this is nothing but the load on the building plus load due to ventilated air that is flowing through the cooling coil plus load due to losses in the return duct. Okay, so you may have return duct losses, leakage losses. You may also have heat addition in the return duct because of the presence of return air fan. Okay, so this plus this has got to be added to the building load to arrive at the total system capacity. Okay. So load on the system due to ventilated air is simply given by, this expression is almost similar to the load due to infiltration. This is equal to, this is a sensible load on the coil due to ventilated air which has flown through the cooling coil. So that is equal to ventilation rate multiplied by this factor, okay, where x is the bypass factor. So 1 minus x is the fraction of this air that has flown through the cooling coil multiplied by specific heat of the air multiplied by the temperature difference, outdoor minus indoor temperature, and this can be written again in terms of flow rate, okay, of ventilation air, that means in terms of meter cube per second. So this is the amount of sensible heat added to the coil because of the ventilation. Similarly, the latent heat added to the coil because of ventilation is given by this expression. Again, this factor considers the amount of air that has flown through the coil, and this is the latent heat of vaporization, and this is the difference between the humidity ratio between the outdoors and indoors. Okay. So if you know the bypass factor and if you know the amount of ventilation to be provided, we can easily calculate what is the load due to ventilation, right. Next comes load on the coil due to leakage in return air duct and due to return air fan. Due to leakage to the return duct and due to return air fan, if there is any fan, it is not necessary that return air duct should have a fan, but in some cases you may have a fan. So if you have a fan, the fan and the leakage adds to the load on the system, so we must consider this. Okay. For example, sensible load due to return duct leakage is given by Q sensible due to duct is equal to U subscript INS into A exposed into T naught minus Ti, where U subscript INS is the overall heat transfer coefficient of the return air duct and A subscript exposed is the exposed area of the return duct. If the return duct is inside the conditioned space, then that need not be considered, okay, because that will not form a load. So since the return air duct size, return air fan capacity are not known initially, a safety factor is provided to account for these. So just like supply air duct, we do not know about the supply air duct dimensions, etc. at this moment. We have taken a safety factor. Similarly, for return air duct and return air fan, we can take a safety factor, and these can be refined when all the loads have been estimated and the duct sizes are known. Okay. So finally, the total sensible load on the coil is simply given by this is the total sensible load on the coil. This is equal to sensible load on the building plus sensible load on the coil due to ventilation plus sensible load on the coil due to return air duct. Similarly, total latent load on the coil is equal to total latent load on the building plus latent load due to ventilation plus latent load due to return air duct. Okay. So finally, the required cooling capacity is nothing but total sensible load on the coil plus total latent load on the coil. So at this point, if you add up everything, we can find out what is the required cooling capacity, so many kilowatts or so many tons. And from the above, one can calculate coil sensible heat factor, coil apparatus dew point, that is coil ADP, and the total supply air quantity. Okay. So all these things can be calculated at this point, and these aspects we have discussed in an earlier lecture. Okay. So this is in brief is a method based on CLTD and CLF. So normally all cooling load calculations, for example based on CLTD and CLF method, a safety factor is always provided to account for various uncertainties in the data used. Okay, so you finally multiply this by a safety factor, okay, to take care of the uncertainties. Thus, the selected system capacity is always higher than the actual required capacity. CLTD CLF method is relatively simple and yields reasonably accurate and economically justifiable results in most of the cases. So, this method is very widely used because of these reasons. However, from economics point of view, for large buildings it is preferable to use more accurate but time consuming methods such as transfer function method or building simulation tools. Okay, if you want to find out the exact cooling load or very accurately, you have to use either transfer function method or you have to actually simulate the building, okay, for estimating the cooling loads. So, thereby you can calculate the required system capacity more accurately. Okay. Next, let us look at heating load calculations. As I said, heating load calculations are fairly simple and conventionally steady state conditions are assumed and internal heat sources are neglected. That means you do not have to bother about solar loads or internal loads. Okay, so you have to consider only external loads due to heat transfer and due to ventilation. And procedure is similar to cooling load. The only difference is that the CLTD value everywhere is replaced by design temperature difference. That means the temperature difference between the indoor and the outdoor, that is T subscript I minus T subscript O. Otherwise, the procedure is exactly similar. And you find that if you are following this method, the calculated heating capacity is always higher than the required. Okay, as a result, you will be actually spending more because the initial cost will be more because of the higher installed capacity than required. But this is safer, and that is why this is conservative. Okay. However, for buildings with large internal heat generation and possibility of storing solar energy, it is always recommended to use transient methods that consider thermal capacity of the buildings and internal heat generation. So, if you are considering the transient characteristics of the building and if you also consider the internal heat generation, you find that the required heating capacity will be much less than what you get by using the steady state methods and what you get by neglecting internal loads. So, thereby you can arrive at an economically justified results. Okay, so this in brief is the heating load calculation. So, let me summarize what we have learned in this lesson. In this lecture, the following aspects are discussed: estimation of internal and external sensible and latent cooling loads on the building, estimation of required capacity of the cooling system, and difference between cooling and heating load calculations. Okay. So, at this point I stop this lecture, and in the next lecture we shall see how to select a suitable air conditioning system. Thank you.